Inductors are also one of the most common devices or elements found in many circuits. It is a passive element designed to store energy in its magnetic field. So compare that to capacitors, wherein it is also a storage device, but it stores energy in electric field. Whereas inductors, it's the storage is in its magnetic field. And it says here inductors find numerous applications in electronic and power systems. They are used in power supplies, transformers, radios, TVs, radars, and electric motors. So the basic construction is it's actually a coil of wire. So if there are coils, then somehow we can say it has some inductive characteristics. So like here, there are many forms, and these are just two that I have drawn here. So we have a solenoid, and we also have the toroids. So somehow, because of that coil, then the magnetic field is actually increased. Okay, so here's the examples or the applications. Electric motors. If you check the inside of these electric motors, there's also a coil of wire. Of course, we are talking right now about ideal inductors because in reality, even I mean the coiling of wire, it also exhibits a resistance. Okay, so it must be an inductor plus resistances. But for now, we are just talking about ideal inductors, so we neglect the resistances. Okay, and then another one, transformers and relays. And the symbol for inductor is this. So we have this coiled wire, and based on the positive sign convention, here it is. Here's the direction of the I, and the symbol that we use for inductor is L. Okay, and the circuit parameter used to describe an inductor is what we call inductance. Okay, so this is the property. Inductor is the device, and the Henry is the units. The symbol for Henrys is letter H. Okay, so in terms of construction, we can determine the inductance based on some formulas or some equations. And as I've said earlier, that there are many forms or types of inductors. I mean, in terms of construction, then this equation right here, I think it only holds true for this type, a solenoid type, where the L all over D, or the length divided by the diameter, is way greater than 10. Okay, so if this is the case, simplest case or most common case that we consider, then the inductance L is equal to the N squared times mu times A all over L, where N is the number of turns. So how many turns we have here? So it is unitless, number of turns times the some property, that is permeability of the core, times the cross-sectional area all over L. And again, even with this expression or equations, we can actually find informations like, for example, the greater the number of the turns, then of course the inductance increases, or the greater the area, inductance increases. So anything above, that's directly proportional, and anything below, then that's inversely proportional. Okay, so now let's discuss how this works. Okay, so the basic principle of how this magnetic field is created is, if we have this wire or a conducting wire, and then we let this current pass through by connecting it through a source, then because of this flow of current across that wire, then this magnetic field actually builds up. Right, so magnetic field is created. So until it reaches its maximum, and then once this is disconnected, then of course the magnetic field will also die down. Okay, so it was also found that when they coil a wire, instead of just having a pure straight wire, so by coiling a wire, the magnetic field actually increases. Right, so here's the magnetic field, so it increases. Okay, and then it was also tried, or maybe experimented, that if we add iron core or some solid materials, especially this iron core, then somehow the field or the magnetic field actually increases some more. So, okay, so that's the basic principle. Because of this flow of current, then magnetic field is created. So what will happen is that once that magnetic field is created, it's not actually the charge that is being stored in that magnetic field. Okay, so unlike in capacitors, wherein the electric charge is actually stored in that device, and somehow that creates electric field. And in that, I mean, uh, let's say if here's our capacitor, recall that there are charges that's being stored here. So plus, minus, right? So we have minus here and pluses on one side. So somehow, once that charge is stored, then it can produce, or it has potential or voltage to be able to deliver that energy. But in inductor, it's not actually the charge that is being transferred into the magnetic field, but rather it's like it's the inertia um, of the magnetic field. Because let's say we have this flow of current, because it is connected to a source, then the magnetic field builds up, right? So once it builds up, and then we we turn this off, or we disconnect this, then because of this magnetic field, it can still, or somehow it can still push the charges along this wire. So somehow it has this inertia, or its ability to be able to still push this current across the wire. So if we discuss it here, in terms of applications. So let's say here's our setup. So same setup as before, except that instead of having a capacitor, we have this inductor right here. So we said, or we always say, that an inductor is a device that stores energy in the form of magnetic field. So how does it do that? So let's say we have this circuit, we have this source, inductor, and this lamp. So if we turn this on, the switch, then there is actually a flow of current, right? So there's going to be a flow of current. So at first, initially, there is no magnetic field yet here. So once this current pass through this coil, and then some of the current will pass across this lamp. So this lamp will light up, and then this one will start building up its magnetic field. So it will start to build up until it reaches its maximum. So once it reaches its maximum, if I turn this off, so let's say I turn this off, I turn this off, then there is no power that's being supplied from this battery terminal. But still, because it has stored energy in its magnetic field, then it's still able to let the current flow across this circuit because of that inertia of that magnetic field, or somehow the push that is being provided by the magnetic field. So somehow at some time, or some interval of time, it is still able to light up. Okay, so without this device, without this inductor, if I turn this off, right away this will turn off. If I turn this on, right away this will turn on. But if we have this inductor device, if I turn this off, then this still will light up for some time interval, because of this ability to be able to still push through the current. Okay, but eventually this will die down because this magnetic field will collapse. Okay, so that's the basic principle. Right here we have a simplified version. So at first, here's our voltage source, our inductor, and our lamp. So if this is off, then no lights on the bulb. But then if I turn this on, then this inductor will start to create its magnetic field. So the magnetic field will build up, and then this will already light up. But then once it gets to its maximum, okay, so once it gets to its maximum, it has fully built up its magnetic field, then we have this maximum, of course, maximum output. And then if I turn this off, so again, so off. So if this is off, then the magnetic field will still die down, but because it has stored energy already, so somehow it can still be able to flow the to push the current. So that's why this bulb will still light up. So until it dies down, then no more lights for this. So now let's talk about the voltage current relationship across an inductor. It says here that the voltage across the terminals of an inductor is proportional to the time rate of change of the current in the inductor. So here's the equation. The voltage is equal to or directly proportional to this rate of change of current with respect to time. This is something like the Ohm's law, but of course it's not. It's not the Ohm's law. But we can see here a derivative, and whenever an equation involves derivatives, then that means that we are going to solve using methods from differential equations, so that we can express. We can also express I as a function of the voltage, as a function of the voltage. But of course, it's a function of time as well, because the magnetic field actually generates once it is connected to a source, and then it also collapses. So that's why we have this something like a transient response. Okay, and for the power in inductors, we still have the same equations. P is equal to VI, and the energy stored is the area under the curve, and recall that P is equal to VI. So I, or the V, so this V, so we can just substitute that, and somehow we get these curves right here. So the I, actually this is just the opposite of the capacitor. So the I is this curve, it's increasing, and then the voltage is decreasing. And if we do some math or derive it using maybe calculus, then we can derive this expression, 1 of L times I squared. So something like the capacitors. Here's our capacitor. Alright, so 1/2 CV squared. So instead of this, the V, this one is increasing for the capacitor, but for inductor, this one is the I. The increasing parameter is the I. Okay, and what else? For the connections in series and parallel, then just like resistors, we can also place inductors in series and parallel. And for the parameters, for the voltage is still the same, for the current is still the same, but the inductance, so it's actually the same as the resistors, that in series the inductance actually adds up if we combine the inductors in series, and this connection in parallel, that means it's a reciprocal property or characteristics. Okay, so I think that's all for our discussions in these inductors. Just take note that we didn't delve into the transient response of this, but rather we're just uh, um, learning the surface of these inductors, because there are actually much things to learn about this. Okay, so now let's go to sample problem, our last sample problem for inductors connected in series and parallel. So here's our problem. It says that find the value of the equivalent inductor that can replace the series parallel connection of inductors shown. So here it is, and we are going to find the equivalent inductance. So it's a combined series and parallel connection already. Okay, so we can notice that this one is in series, and the equivalent of this inductance, let's say LE1, this is in parallel to this L2, right? And then series. So somehow we just simply apply these equations or these properties right here. Okay, so to do that, So for this solution, so number one, let's solve for, let's say L. Let's just substitute right away. So L3 and 4, what's the combined, or LE4, 3 and 4. Okay, so L3, 4 is equal to L3 plus L4 because they are in series. So 2 plus 4. So 2 plus 4, and we have 6 henries. Okay, next one is, if we draw this, so here's our L3, 4. So L3, 4, and that is 6 henries. This is I think this is still L2, and L1. This is 3 henries and 1 henry for L1. Okay, so now let's solve. We'll be solving this. Okay, next is let's solve for equivalent inductance for 3, 4, and 2. So if we do that, L, these are in parallel connection, so therefore 1 over L, that's going to be 1 over 3 plus 1 over 6. Okay, and if we do that, this is, so 1 over 3 plus, okay, so plus 1 over 6. So this is 1/2, and then 1 divided by the answer, this is 2. So this is 2 henries. Okay, so now we have a series connection. If we draw this, so L1, 1H, and L, let's say 2, 3, 4, this is 2 henries. Therefore, the total inductance is just simply 2 plus 1, so this is 3 henries. Okay, so I think that's all for our inductance or inductors. So in summary, we have here a table tabulating the resistor, capacitor, and inductor, and the parameters or the relationship, such as the voltage and the current relationship, the IV relationship, or the power, or for the series connection and parallel connections. Okay, so for resistors, recall it's just simply V is equal to IR, right? And for capacitors, since this is our main equation, or that I've shown you, so if we solve this using differential equations, then we can solve for V. For inductors, here is our main equation, and if you solve for I, then you can solve this, or you can derive this expression. And for the power or the work, for resistor, this is just simply VI, or I squared R, or V squared all over R. And for the capacitor, we have this C times V squared, and for the inductor, that's L times I squared. And for series, so the series R1, R2 just simply adds up the resistance, which is just the same for inductors, but for capacitors it's the reciprocal. So that's just one way of writing when we have only 2 capacitors. And for parallel connections, here's our reciprocal characteristics or expressions, and the same as this, and still other information. And also it says here circuit variable that cannot change abruptly. So that means because just I mean for capacitors, it will take some time to be able to store energy in the capacitor, and also it will take some time to drain that energy from that capacitor. So once we want to use that energy, then also it will take some time. So that's why it says here it cannot change abruptly, or sometimes it is stated that the capacitors, it's a device that resists any change of voltage, and of course it means instantaneous voltage because it cannot change abruptly. Whereas for inductors, the circuit variable that cannot change abruptly is the current. Okay, so that's the I, because it will take some time to be able to build up the magnetic field, and once it builds up, then of course it wants to push the the amperes on that wire, so it cannot just change suddenly or abruptly. Okay, so I guess that's all for our topics in this capacitors and inductors. So in the next video, we'll be moving on to our next topic on AC systems. So see you in the next video.